as well. This week we have Prashant Vasudevan, who is a postdoc with Sanjam Garg at UC Berkeley, and will be telling us about cryptography from information loss.
Yes, hi. Thanks a lot for having me. Yeah, like Sarah was saying, I'm going to tell you about this work that we did last year sometime, studying information laws and cryptography. It was done with a lot of different people, as you can see here. And the starting point for all this was this postulate, right, that cryptography is essentially hardness with structure. To do any kind of cryptography, to get from even the simplest primitives like one-way functions all the way to a functional encryption, whatever you want, you need a hard problem with sufficient structure, right? And when I say hardness, it is somewhat clear what I mean. It can be a worst case hardness, average case hardness. Maybe there are some other variants, but it's more or less clear what I mean. But what do I mean when I say structure, right? There are lots of different possibilities and lots of different dimensions for what I could mean when I say structure. For example, we know like all these group-based problems like DDH, they have this algebraic structure. And these lattice problems have this kind of geometric structure that we're able to use. And what I want to ask here is what sort of structure is sufficient to do different kinds of cryptography, to get one-way functions, to get other things. And this question, either explicitly or implicitly, has been answered several times in the past by different people. And for example, Ostrowski in 91 showed that if you have languages which have statistical zero knowledge proofs, whatever statistical zero knowledge proofs, then this can be combined with average case hardness to get one-way functions. And Ostrowski and Wigderson also showed that you can combine the same thing with worst case hardness to get a weaker form of one-way functions. And there has been work in different directions over here showing that different kinds of structure can be used to start with different kinds of hardness to get different cryptographic primitives. And what we do in this work, what I'm going to tell you about in this talk, is our work in providing a couple of new answers to this question, to the question of what is sufficient structure. And in particular, I'm going to tell you about these two kinds of reductions called lossy reductions and compressing reduction that we have found that you can use to start with worst case hardness and get one-way functions, or to go start with a certain kind of average case hardness and get collision resistant hash functions. And this is what I'm going to tell you about, and this is how the talk is going to be. I'm going to start by telling you what these lossy or compressing reductions are, and what is sort of known about them, what connections to cryptography is known about them so far. And then I'll tell you about how to get one-way functions using these things. And this will involve discussing certain different kinds of average case hardness and how they relate to each other. And after that, I'll tell you a little bit about some interesting open problems that come up from this study. And then if we have time, I will tell you about how to get collision resistant hash functions from different starting conditions. And so there are going to be a lot of concepts that I'm going to keep introducing throughout the talk. And if any of them are not clear at any point, please feel free to stop me and ask for clarifications. I'm happy to. There should be some flexibility in terms of time, so it should be okay. So yeah, so to make sure they're on the same page, let's start with by saying what I mean when I say reduction. Right? By reduction, I mean a randomized polynomial time reduction that may have some error. For most of the talk, I'm going to be ignoring this error, but this is what I really mean when I say a polynomial time reduction. It has some error. So reduction from L to L prime is this algorithm R, such that R of X is in L prime, if and only if X is in L, with high probability. So to start with, a compressing reduction, which for some function t, is a reduction which physically shrinks the size of its input. Right? So this R of X, the number of bits in R of X, is at most T of n for any input of size n. And you can think of T as being a sublinear, as being something smaller. T of n is smaller than. So this is a compressing reduction. And this is a concept that comes up very often in different forms in parameterized complexity. has been widely studied in various settings. And you can see some very simple examples.
Prashant, just to make sure, the probability is taking over only the coins of the reduction, right?
Oh, yes, yes.
With okay, thanks.
Yes, it's for every x, all the random coins of the reduction. Yeah.
Okay, thanks.
Yeah, so composite reductions, you can see some very simple examples of things like this, right? Where you can take any problem in P, and it has a one composite reduction to a trivial language, because you can just decide the language and output 1 or 0. And there are some very interesting non-trivial examples of these reductions that have been found to be very useful in the past, very interesting to study in the past, such as problems which are parameterized, such as a vertex cover, for example, which has this very interesting reduction where you can take a graph which has and some parameter k, and then you can perform this reduction to get a new graph that has a vertex cover of size k, if and only if the original one had a vertex cover of size k, and the new graph has size that is poly in k, and is independent of the original size of the graph. Right? So these reductions come up very often in the study of parameterized complexity, and these are composite reductions where you physically decrease the. What we are going to be talking about for the most of this talk is lossy reductions, which are allowed to have output length that is larger than the input length, but still lose information about the input in this sense, right, where you have this reduction R. And now you take, you fix your input length N, and take any possible distribution over inputs from this, of the size. And then what I want to say is that the reduction reveals at most T of n bits of information with this prior distribution over the inputs. In other terms, if you take an input distribution that has very low entropy to begin with, I don't care what the reduction does on it. Basically, it could reveal anything about the input that it wants. But if I take an input distribution that has large entropy, then it still maintains that some amount of entropy. Almost T of n bits of information about this input is leaked by the reduction, right? And this it's similar to the definitions of like information complexity and communication complexity and all. And this is the notion of lossiness that we're going to be using, right? And to illustrate this kind of lossiness, let's take again a couple of examples. One example is any random self-reduction. Right? If you take what is random self-reduction, it's where you take an input x for some language, instance x for some language L, and you reduce it to a distribution over inputs. So you reduction samples from a distribution, such that if x is in the language, then the output of the reduction is also in the language, and is always from the same distribution, independent of which input you start. Right? And the same for if the input is not in the language, it's a different distribution. These reductions, they reveal at most, more or less, at most 1 bit about the input, which is whether it is in the language or not. And such reductions are one lossy because they reveal at most 1 bit about it. And again, you can see some non-trivial examples of this. For example, take a language like this, where I give you a matrix, an Ambient matrix, and ask whether its determinant is 0. So this has a polynomial time algorithm, but for now, pretend that you don't know that you don't know this is a polynomial time, and consider the following operation, right? Where you take this matrix and multiply it with a random full rank matrix, and this gives you this sort of randomized matrix that doesn't look exactly like him, doesn't reveal everything about him, but still has the same span as him, right? And you can show that this reduction, whatever this reduction, this self-reduction, it loses like a constant fraction of information about the matrix. And so you started out with n squared log of bits in the, and you are losing everything except n squared of log of bits. Or rather, those many bits are being removed. Yeah, so these are lossy reductions, and this is what we are going to be talking about for most of this talk. And these are related to and generalized a number of different concepts from different parts of
Before you move on, I managed to confuse myself. So in let's say random self-reduction, I'm reducing the worst case in a worst case instance to an average case instance, which means if I can solve the average case, then I can solve the worst case, right?
Mm-hmm.
So L is the worst case, L prime is the average case. But in the previous slide, you also talked about reducing from L any language to L prime the trivial language, which doesn't help me solve the original. Like then in that case, solving L prime doesn't help me solve L. So are the reductions in the same direction in this case?
Could you say this again? What do you mean it doesn't? If you have a reduction to the trivial language, that means you've already sort of solved the L. That's all the problem.
Ah, great, cool. Reduction solved membership, basically. Yeah, cool.
Yeah,
Great.
yeah.
Okay, cool.
So, if there are any other questions, I'm happy to clarify now.
Just out of curiosity, do you have any intuition for where the 1/4 comes from in the matrix example? Just out of curiosity. If you don't know, no worries. It's like not at all the focus. I'm just curious. I can see where the n squared kind of comes from. I can see where the log f comes from, I think.
So I can tell you how you get this. The way you get this is you calculate the number of different possible vector linear subspaces of the space. And then for each of those, it's like, so like I said, right, this process, it essentially randomizes this matrix completely up to maintaining the same span. And so it basically divides up all matrices into these equivalence classes based on the vector space, the subspace that they span. And if you count those and take the log of that, that is this number.
Interesting. Thanks.
So by the way, so here the randomness again is now chosen over the inputs, right? But now it's random variable x, and I guess this is over the uniform distribution over all inputs, or what is exactly the information? How do you what is the randomness over the inputs here?
Yes, random. What I ask is that this inequality. Can you see my mouse, by the way?
Yeah.
So what I ask is that this inequality, it holds for every possible distribution of the inputs. Any distribution that you take, and you measure this mutual information, it should be bounded.
Okay, so I'm trying to interpret this with respect to the problem above of the matrix determinant. So that means that whatever distribution I choose over matrices, the reduction, but this information, this inequality holds.
Yes, exactly. Whatever distribution you choose over matrices, it reveals at most these many bits of information. And the reason again is that the only thing that this reduction could reveal is what vector space the original matrix span. And this is a lower bound on like the log of the number of possible vector spaces. So whatever distribution you take, the reduction cannot be revealing more than these many bits of information.
It's an upper bound.
Yeah. But yeah.
You're saying the number of linear subspaces is at most 2 to this number.
Yeah.
So
the information that is revealed by the reduction can be captured by just saying what subspace it is, and so you can be revealing at most these many bits. Even though the output of the reduction is the matrix, which has more bits than this. Is that okay?
Okay. Yeah.
Okay. This is it's a difficult concept to get a handle on because it doesn't really. It's not. How do you say? It's not. It doesn't relate to anything on the ground, sort of, right? Like there's no prior on X that you specifically care about. So it's. But yeah, this is not.
Do you have a definition of the information somewhere? Just to have it. I don't have it on top of my head. What does this I mean?
That's your conference call. Go ahead. That's just mutual information, right?
Yeah, definition of mutual. Yeah, so I'm trying to remember what it is. Okay, I'll figure it out.
So actually, Prashant, how different is this from just restricting the range? Like all the in the example well, I guess not. Maybe not for like in the examples you have, the output distributions are always like uniform over equivalence classes, of which there are just not very many.
The output distributions are not necessarily uniform, but it is splitting it up into equivalence classes of which there are not.
Sure, sorry. It's a mixture of well, in your case, they really are like uniform within each equivalence class. Like,
yeah.
You know, it's either a uniformly random matrix with the right span or a uniformly random number with the right residuosity, right? Like, are there examples where that's not the structure? Like, effectively, if you had time on your hands, in all of these cases, you could actually output a shorter thing.
This is true.
And in fact, for the rank thing, you could totally do it in polynomial time, but not, you know, not so much for quadratic residues. But
yes.
For any reduction that's not perfect, it might might not break up in the way that Adam just described, right?
I cannot think of a good example where it's not divided up into equivalence classes like this. Like if you don't care about the amount of time it takes.
And the question, maybe it will become clear later, but why do you choose to use the information? It's a natural. Is there any specific reason to use this particular measure, or?
Mostly because it's natural and it seems to sort of generalize the things that we started out with.
Okay.
You can try to use other measures of information as well. And the kind of things that I am about to prove will probably still hold. And in fact, if you use something more stringent, you might be able to do more.
I see. Okay.
Okay. So yeah. So this, I hope it's at least sufficiently clear. And let's move on. So yeah, this is a lossy reduction. The reduction reveals at most 3 bits of information about the inputs, whatever the prior distribution is. And this sort of, it's related to and generalizes a number of different concepts from across computer science, like kernelization, for example, which is this concept from parameterized complexity, where you compress problems according to some parameter, like the vertex cover example I said earlier. And there's this notion of instance compression, where you take a problem, take an NP problem, and reduce it to a size polynomial in just the witness length. And there are randomized encodings, which are effectively just one lossy reductions to some language that you don't really care about what the target language is. It's to some language. And of course, there are relations to these average case carp reductions, which is very reduced to a specific language. And all of these are sort of captured by these lossy reductions, some of these by compressing reductions as well. And in fact, there have been even with respect to the relations to cryptography, these reductions have been studied in the past. And in particular, the reductions that were studied in this context were for languages of this specific form, right? Where you take, you construct this composite language, where you take a language L and you compose it with the OR function. Say you take M instances of for L and ask whether there exists one of these instances which is contained in the language. So this is this OR composed with L. And typically we will be thinking about reductions from this language, from languages of this form to other languages. And as an example, again, you can take the language we talked about earlier, where I give you a matrix and ask whether the determinant is 0. And you can see that it has this very nice, there's this very nice compressing reduction from OR of this language to itself, right? Where you take all these matrices and just multiply them. And this shrinks the input by a lot. And you can see that the determinant is 0 in the end, if and only if there existed one whose determinant was 0. Right? And this is like this much compassing reduction for or of this language to this language, etc. And we'll be thinking of languages of reductions like this. And the point where this whole study started, where whatever we were thinking about started, was in this work of Harnick and Nowell from 2010, where they showed that if you had a reduction for all SAT, if you had a compressing reduction for all of SAT, where you compressed from m instances of size n to something to an instance of size poly in just n independent of m, then they showed that this kind of a reduction can be used to get collision resistant hashing from one-way functions, right? Which would be a big deal. We still don't know how to do this. But unfortunately, soon afterwards, Fortnow and Santhanam showed that, in fact, a reduction like this would give you like perhaps much more surprising consequences and probably cannot exist. That it would actually imply that the polynomial hierarchy collapses. And this was, and this sort of culminated in this work by Drucker, who showed something even stronger, which was that even if you take a slightly weaker reduction from some language, take these reductions were poly of n, right? You had to be independent of m. But Drucker said, take a reduction which takes m instances for L and does a compressing reduction for R of L and compresses only to something of length m times log n. Right? In particular, you could still be revealing something about each of the inputs. You could still be revealing like log n bits about each of the instances you took. Let's say you have a reduction like this from R of any language L to any other language at all. Then this L is contained in this class called SZK. Right? In particular, SZK is not believed to contain NP-hard problems because that would imply a polynomial hierarchy collapse. So this sort of implies the previous results and does something much stronger. And this was our starting point. Our starting point was the observation that this holds not just for compressing reductions, but also for lossy reductions. Right? And at this point, I'm going to tell you about what SZK is and what this result effectively implies. Right? So this class SZK is the class of problems which have statistical zero knowledge proofs. And I'm going to tell you only about the complete problem that characterizes this class, this problem called statistical difference, which takes two circuits as input and asks whether the distribution that is sampled by these circuits, you give these circuits random input and look at the output, and asks whether the distribution that is thus sampled is either close or far. Right? So if they're far, there's a no instance. If they're close, it's a yes instance. Right? And the interesting thing to keep in mind about this is this result by Ostrowski that I mentioned earlier, who showed that if you have an average case hard problem in this class, that implies the existence of one-way functions. Right? So this is this class. And now you take this result by Drucker, right, who said you have this reduction from all of L to anything and implies at least on the ZK. You can see that this, along with what I just told you, implies that if you had such a reduction for a language L, and this L happens to be average case hard, that immediately implies one-way functions, right? Because it's an SZK and it's average case hard, so one-way functions. And the first result that I'm going to tell you about is what we were able to show. Is a sort of strengthening of this, which says that if you take something a little stronger in terms of the reduction, if your reduction is a little more lossy than this is like m over 100 lossy, and the reduction is from R of L to itself, then you can in fact make do with worst case hardness and still get one-way functions. All right, so this is what I'm going to tell you about next. Are things clear so far, what the statement means? Okay.
So just to understand, so the difference between the new thing in the red is that the lossiness is going to be more than the number of instances, right? Right. It's m over 100 lossy, where right.
Yeah, it's weaker in that sense. In that we are asking for something stronger. We're asking for a more compressing, for more lossy reduction to start with. So the hypothesis is stronger. But we are also able to use worst case hardness. Yeah. And the other difference is that you have to reduce from R of L to itself. It has to be a self reduction.
I see. Okay.
If if on the left it said L is average case hard, then you wouldn't need, then this would be implied by the Drucker result, right?
Yeah. Yeah.
Okay. So it's the switch to worst case hardness requires you to strengthen the Ostrovsky result, or the Drucker plus Ostrovsky result.
Yeah. So the left box is worst case hardness is a better hypothesis, is a weaker hypothesis than average case hardness. But what we ask of the reduction is a stronger hypothesis than what was asked of the reduction.
Right. So the bottom one, what are the requirements on L prime in the Drucker result?
Nothing at all. It can be anything.
I see. Even very hard language.
Yeah, it can be arbitrarily hard language.
Okay.
But yeah, what we require that it's the same.
Okay.
Yes.
Is there a language for which such a reduction is easy to show?
I
mean, just existence of reduction. That's
R of L to itself.
Yeah.
There were examples I mentioned earlier with the matrices and
determinant. Okay, yeah.
You can do some things with certain lattice problems. I'll say a little bit later on, but not to this extent.
Okay.
Yes. Okay. So let me tell you how we do this. Right? And you start with what I just said with Drucker's result, that this implies that L is contained in a ZK. This is a stronger hypothesis than what Drucker was using, so this still follows. And then we do this other thing where you show that these two things together imply that L has a certain kind of average case hardness, which I'm going to tell you about in a minute. And then we put these two together to show that a language in SDK which has this kind of average case hardness, this one-sided average case hardness, implies a one-way function. And I'm going to start by telling you what I mean by one-sided average case hardness and how this implies that. And to do this, I'm going to start by discussing the different kinds of hardness we typically talk about for languages, right? So the simplest is worst case hardness, where you say that for any possible algorithm, there is some input on which it is wrong. Any algorithm that's trying to decide this language is wrong on some input. The next level of hardness that we usually talk about is average case hardness, where you switch the quantifiers and say that there exists a distribution over inputs such that for any algorithm you take, it is wrong with some probability over this distribution. And so you sort of fix the distribution over inputs before you fix the language. And this is a stronger notion of hardness than worst case hardness, and it implies worst case hardness. Yet another notion of average case hardness, which I will call two-sided average case hardness, is a stronger version of this, where instead of saying that there exists this one hard distribution over inputs, you ask that there are two hard distributions. There are two distributions, one over no instances and one over yes instances, that you can sample separately, right, such that these two distributions are indistinguishable. And again, this is stronger than plain average case hardness, where you have just this, or you have a sampler for just this one hard distribution. You may not be able to sample these yes and no distributions separately. And what I want to consider is sort of some intermediate thing between these things that I call one-sided average case hardness, where I want to sort of, instead of flipping the quantifiers from worst case hardness, I want to sort of split the quantifiers, where I say there exists this one distribution over no instances, such that any algorithm A has some distribution over yes instances that it cannot distinguish from no instances. Right? So again, there's this one fixed no distribution, but for every possible algorithm that's trying to decide the language, there could be a different yes distribution that it cannot distinguish from this no distribution. And this, you can see that this is sort of is implied by two-sided average case hardness, and it also implies worst case hardness, but it's not really clear how it relates to plain average case hardness on that. And this is what we are going to be talking about for the next so much time. Is any questions about this?
Again, so I'm trying to, sorry for being slow, I'm trying to digest this notion again. So again, what does it mean? It means that the existing distributions on no instances, such that, again, so there is what? Such as for any algorithm, the existing distribution on the yes instances, and then this, I don't understand why this indistinguishability, what does it mean? The probability that the algorithm says, so why is this in,
Can I ask?
yeah, yeah.
Can I take a stab while Ron?
Yeah, please go ahead.
I'm trying to understand, like this exists a distribution over yes instances. Does that distribution ever have to be complicated? Like, wouldn't it in general just be like a distribution over like two inputs or something like that? Like that, this Y doesn't have to be like computationally easy to find, right? Like it just has to be.
It doesn't have to be.
It itself should be simple. Like the distribution Y should be sampleable in some like non-uniform way or something like that.
No, or it doesn't have to be sampleable also. At least for our results, it doesn't have to be sampleable.
So suppose I pick my, I guess it seems like very similar to saying like there's a no distribution such that, you know, I can find two yes strings where one of them, the weight is, the acceptance probability is below, like let's say P is the acceptance probability on the left, right?
Mm-hmm.
Isn't the condition on the right hand side is equivalent to saying I can find two strings where one of them the acceptance probability is below P and the other one the acceptance probability is like above P.
Yeah, it's effectively that. Yeah.
So like these Ys, they are like in the word, you know, they could just be distributions on like pairs of strings. They don't even have to be like super complicated.
Yeah, they don't have to be more than that.
Yeah.
So,
So this two-sided average case, it's much stronger. It's really like it's the statistical zone knowledge, right? There are two distributions on yes and no that are really indistinguishable to the algorithm. Right? So that's a really strong requirement, right? The two-sided average case.
It's pretty strong. In fact, the existence of a language that is two-sided average case hard is equivalent to the existence of one-way functions.
right. It's like you can sample a solved puzzle, right?
It's statistically zero knowledge, right? Or whatever. Yeah, that's
Wait, you're saying it's the same as statistical zero knowledge?
Well, you know, that's what they use. That's a complete language for statistical zero knowledge, right? In some, not far. You might forget that. Forget statistical zero knowledge. Yeah, but anyways, so the one-sided average case, there is also the symmetric case, right? You flip the yes and the no in the order of quantifiers. Is that the same, or is there a real difference there?
It's sort of complementary to this. So like I'll be proving that if you have an OR reduction and this kind of one-sided average case hardness, you have some implications. You can get the same implications with the other kind of one, with fixing the yes distribution and the reduction. So sort of complementary.
Right. It's like the whatever.
I see, because the thing you're reducing from is not symmetric, not nicely symmetric because of this OR condition, right?
Yeah, or rather the language isn't nice. Yeah, actually, yeah, because of the OR condition is not symmetric. Yes.
And so so it's fine. Like neither one is symmetric, right?
Yeah.
Okay.
How much weaker is this one-sided average case than? You're saying it's incomparable? to the left-hand, the regular average case notion?
Yeah, as far as we
On the
can
way
tell,
on it?
we can't find any relations.
I see.
Because on the left, you want the D to be sampleable. So with that, I don't know what to do.
Mm.
Oh, I see.
Prashant, you said that the two-sided average case implies one-way functions, but these distributions are not efficiently sampleable. Isn't it more like heuristica than one-way functions?
Oh no, so actually I do want them to be sampleable. That's what I meant. The only thing I don't care about being sampleable is this YA.
Right. We can.
I see. So n for the one-sided, you do want an efficient distribution on n on the no instances.
Yes.
Oh, okay. Thank you.
Yeah, I want n to be efficiently sampleable. YA I don't care.
Well, YA, like you want to, well, I guess there are two kinds of questions. One is like, is the YA you find like efficiently sampleable, and is there an efficient way to find YA?
Yeah.
Right.
Yeah.
Those are like different questions.
Neither one, I guess, right?
Yeah, and I don't care about either. Yeah.
Right. I think you can get one of those for the easy one. You can get for free.
I guess Adam is saying YA might as well be just a distribution over two values, so it's sufficiently sampleable.
You can just like write it down. Well, at least in a non-uniform sense. It's
Yeah, that's true.
Y2, maybe one.
cool. Thanks.
Yes. So yeah, so this is one-sided average case hardness. It's weird, and yes, it is weird. And here's what I'm going to say about this, right? I'm going to start by saying that if you have a worst case hard language and a reduction from or of that language to itself that is lossy, then you can in fact show that the L is one-sided average case. Essentially using the kinds of things that Drucker proves in the result that I will. And how do you do this? Very quickly. So here is an outline of the proofs. So you have this reduction from L to itself, from or of L to itself, which says if there exists an input which is in the language, then Y is in the language, otherwise not. Let's say it's perfect for now. And it's also lossy. The sort of idea that we are going to use is that since it is lossy, there has to be some information about some of the xi's that is lost by Y. Like it cannot that much information. Y cannot contain that much information about all of the xi's. It has to forget something, right? And this is sort of captured by this very nice, very pretty lemma by Drucker that he calls the discasing distribution lemma, which says the following. Okay, he says, okay, you take this reduction R and consider taking all this. It takes our inputs x1 to xn. You take this language L and take any x that is not contained in L, right? And you plug it in to a random position in this in the inputs. Right? Consider doing this. There exists a distribution D, one fixed distribution D for the language, such that for any x that is not in the language, if you do this, and if you sample all of the other inputs from this distribution, then the distribution of Y that you get as an output is more or less the same, is independent of which x you take. For any x not in the language, you get the same distribution for Y if you do this procedure.
So there exists an index I? That's
for a random index I.
Sorry?
For a random index I. So the experiment is you pick a random I, put your x there, and all the other x's inputs you take from this D. And you run the R and you get the Y.
What, I don't understand. What if Y, oh, I see, M over 100. So Y can't just be equal to x1.
Yeah, that's the point, yeah.
I see. So if it said M, this wouldn't be true. Or even something.
Yeah.
Okay.
If it's M, this would...
Oh, sorry. No, if it said N, this wouldn't be true. You could just output one of the instances.
If it's at N, this would sort of be true with, it depends on what I mean by almost the same. Like even if it's N, even if I say always output the first thing, you always output x1, the probability that I put my x at x1 is still quite low.
I'm still I'm confused about what this statement is saying, Prashant.
Okay.
What's L here?
So L here is this language, and this R is a reduction from R of L to L, which says that it takes these M inputs.
I'm trying to understand just the statement of the lemma. There's a distribution D supported on L bar, which the distribution of Y above, like that's. Oh, I see. You're saying take this reduction and generate inputs in the following way. Fix one of the X's and generate all the others from this D. And you get.
Yes.
What's the quantifier over I here?
Say again?
What's the quantifier over I? Is I selected randomly or something like that?
Yeah, it's random.
Yes.
Or
you probably said that. It just went too fast.
Yeah, you pick a random I, put your X there, everything else you sample from D, and you look at the output.
Mm.
And the lemma says that it doesn't matter which X you take, the output looks the same, as long as X is not contained in it.
Let's say I had such a reduction, and then I created a new reduction, which just output Y concatenated with whether X1 is in the language.
Mm-hmm.
Right? That would still satisfy the hypothesis. Like it would be slightly less lossy, but whatever. But wouldn't that extra bit totally violate the lemma?
No, this particular bit will definitely not, because this is only for X that is not contained in. So that would always be 0. So but even if it was some other bit, it would still not violate the lemma, because the probability that I choose I to be that is quite low. And when I say almost the same, I don't mean negligibly close. I mean close to some small constant.
So if X is in the language, then Y would be in the language, and then maybe the distribution of Y really depend on everything, right?
Yeah, if X is in the language, then all bets are off. Not saying anything.
Okay.
Okay. Is the lemma saying that the distribution of Y above is almost the same no matter what X in not L you pick, or is it saying it's almost the same no matter which I you happen to randomly choose?
It's saying no matter what X you happen to pick.
Okay. Okay.
Okay, anything else? Okay, so yeah, let's say we understand this lemma, and what we are going to use is this distribution. So we wanted to show that if such reduction exists, then L is one-sided hard if L is worst case hard, and we are going to sort of use this distribution over Y as the node distribution for the average case, one-sided average case hardness of L. And here are a couple of observations about this, right? First, if you take this distribution D0 of Y's that you get if you take an X in L bar and sampling this D, etc., then it's contained in L bar, right? It's not contained in L. On the other hand, if you do the same experiment with an X that is contained in L, then Y is contained in L, because this is a good OR reduction. And so you can now you can sort of argue like this, right? Let's say that L is in fact worst case hard. Then for any algorithm that is trying to decide L on average, there has to be a distribution over inputs in the language that A cannot distinguish from D0, right? Because if it happens to be the case that there is some algorithm which distinguishes any possible yes distribution from D0, then using this reduction, it can also be used to decide the language in the worst case. You just plug the X in here, get the Y, give it to that. And so this shows that L is in fact one-sided average case hard, and with D0 as the node distribution. Right? So this is one part of the proof. And in terms of the other part, also you sort of use the same lemma to get just like Tucker did, which is, and you make the argument the following way, right? Now I want to show that if L has this kind of OR reduction to itself, then it's contained in SDK.
Prashant, this distribution of L that you had there, is it efficiently sampleable necessarily? No, right?
This is non-uniformly efficiently sampleable, yes. Uniformly, I don't know what to do. Non-uniformly it is.
Okay.
And this is in fact what Drucker shows, that you have this distribution that you can sample non-uniformly that has this property.
Where the there exists, the reason it's not for all distributions of RL, it's, oh, I see. The there exists comes from the there exists in the worst case.
Yeah.
Like it's the yes instance that is hard for the adversary, for this particular adversary, right?
Yeah, effectively, yes.
Defined by this yes instance.
Yeah, that will be at least that distribution you cannot distinguish. Yeah.
Mm.
So L is one-sided hard. Okay. How do you show L is in SDK? Well, you can use the same thing. If again, the lemma says that if X is contained in X is not in L, then Y is close to D0. If X is in L, then it has to be far from D0, right? Because D0 is supported outside L, but the output of R if X is in L has to be in L. And so to reduce to statistical difference, you just output these two circuits, one which samples D0 and one which actually does this reduction. And then by the above observations, you can see that this is a reduction to the complement of statistical difference. And this shows that L is in SDK. Right? And in the interest of time, I'm going to move on. So far we have said, we have shown these two things, that if you have these two conditions, then L is both one-sided Average case hard and L is contained in the SDK. How do we show that this implies one-way functions? It's again using this statistical difference as the complete problem for SDK, which I'll briefly describe now, and then we can end after that. So I want to show this. I want to show that this language, if it is one-sided hard, then one-way functions exist, right? And I want to say that if you take this no distribution n, then you can construct, in fact, the one-way function in the following way, where your function takes this bit b and some input x that you're going to use later, and some randomness r, and you sample from the node distribution using this randomness r, and then which gives you these two circuits, C0 and C1, and then you just output a sample from one of those two circuits, which is determined by this bit b. And I want to claim that this function is not exactly a one-way function, but is what is known as a distributional one-way function. If statistical difference is in fact one-sided hard, then you cannot sample random inverses for this function. I give you some C0, C1, and CB of x. You cannot sample a random B, X, R, which gives you this. And it is known that the existence of functions like this is equivalent to the existence of one-way functions. And so why is this true? What happens if you are able to, in fact, take this function and sample random inverses? Well, we have to show that you can use that to break the one-sided average case hardness of statistical difference. And you do it in the following way. You do it by sort of considering like an, what do you call it? The same function, but instead of using the node distribution, you use some distribution y over s instances. Consider what happens if I take a function fy like this, and then try to run the inverter on that, right? And we have the following observation, that if you have two circuits that are far apart, then this bit b in the inverse of this function f or fy is more biased if they are farther apart, because it's if they're farther apart, then knowing cb of x tells you more clearly what b is than if they were close. Like if they were disjoint, for example, then knowing C0, C1, and CB of x completely determines what B is. Whereas if they were the same distribution, then knowing CB of X tells you nothing about what B is. Right? So if you did indeed have this random inverse sampler, then you can check, you can give it an output from F or Fy and see whether it's able to give you the same B that you used as input. And if you had given it a sample from F, an output of F, then it is simply more likely to give you B, as opposed to if you had given it a sample from Fy, an output of Fy. And this lets you distinguish between N and any distribution Y over S instances, which is a contradiction, which breaks one-sided half-case hardness.
It almost sounds like you can build collision resistant hash function also from that.
From this,
but just intuition. Finding another image.
Finding another image. I think the thing that's in the way of doing that is the fact that collision resistance, you sort of want, if you want actual collision resistance, it's a sort of this worst case notion, right? I don't really have control over. It's not like I give you one input and then you find another thing.
Right.
Like you have the freedom to choose any two inputs that collide.
Yeah.
But you can't get the second image resistance with this.
Right. Yeah, it's not clear what would be the family here, but yeah, I don't know.
Yeah, that worst case thing is basically what, because these things are not perfect. Like if you had certain perfectness conditions here and there, saying like the reduction is saying instead of 2/3, 1/3, if it's like perfect, if it's 1 or 0, things like that, then probably you can get something. But with this error being around, I don't know how to get collision resistance from this because of this worst case thing. Yeah, so this is how we get function, and I'm almost out of time. So I am going to very quickly just tell you that these are the other results that we get. We can get one-way functions from certain other incomparable kinds of lossy reductions. And you can get collision resistance from slightly stronger lossy reductions and from this one-sided average case hardness plus some other conditions. And
do each of these, for the top three, I guess, do each of them go through one-sided average case hardness?
For the first one is what I described. And the second one actually goes through like things that look like more like randomized encodings, things that look more like two-sided average case hardness, where you use essentially the same techniques that you use to show that OR reductions imply one-sided average case hardness, and you apply it to majority, and you can use it to show that actually implies two-sided average case hardness. The third one is it uses sort of different techniques. In the third case, you're essentially able to show that the reduction itself is a one-way function. And for collision resistance, again, it's a completely different way of doing things. For collision resistance, if you know about this, it's like how you get collision resistance from additive homomorphic encryption. It's effectively the same thing. Yeah, so these are the results, and I was about the one other thing that I wanted to say, which I will not get into now, is that this raises some very interesting questions. It raises some very interesting possibilities for approaching. In fact, I will say a little bit about this now. So one interesting concrete question that arises from this that I'm very interested in, that I don't know really how to approach, or rather how to solve, is this question about getting one-way functions from the shortest vector problem over lattices, right? So what is the shortest vector problem? What is the gap shortest vector problem over lattices? It's where I give you this basis of a lattice, and I give you this approximation factor gamma, and I tell you that either this lattice that I told you about has a vector of length less than 1, or all vectors are of length at least gamma of n, where n is the dimension, right? This is this problem. And we know how to get a whole bunch of cryptography from the hardness of this problem. In particular, if you look at, in particular, we know how to get one-way functions in a certain regime of this gamma. So you take the different possible values of gamma. We know that if you start with an approximation factor of more than something like n, theta, n log n, something like this, then you take the worst case hardness of gap SVP with this gamma, and we know how to get one-way functions from that, and the worst case on all of this, right? And we also know that if you start with approximation factors larger than square root n, these problems are contained in SDK. Gap SVP with this gamma is contained in SDK due to this work by Goldrick and Goldwasser from a long time ago. And in between these, we do not know. In between these, we know that if you start from average case hardness, you can get one-way functions simply because they're contained in SDK. But from worst case hardness, we do not know any crypto. And sort of one thing that, one problem that I'm very interested in that I'm hoping will be approachable is of somehow trying to expand this, trying to push this, this green line a bit more towards the left using these compression techniques, right? And why do we think these stand any chance? Because see, what do we want to do in these lossy reductions and consistent reductions? We want to take a bunch of instances of this language and of gap SVP and do an OR reduction to another, right? I want to come up with a new basis that sort of has a short vector if and only if one of these things are a short vector. Well, it feels somehow like lattices have the kind of structure that may let you do something like this. In particular, if you just take this B to be like this block diagonal matrix with all of these BIs, that has this property. Like it doesn't compress, but it is an OR reduction, right? So there is this structure that sort of allows you to do OR reductions by combining these bases in some way. And the question that I want to ask is it possible to sort of use these properties to get what we want here? In particular, can we get a reduction with with the gammas on both sides working out in the right way, and also like that's also compressing enough that you can use the connections that I just showed you now to somehow extend this green line a bit more to the left and get cryptography from the hardness of slightly harder gap SVP problems. Yeah, so this is the one problem that I want. This is the one open problem that I really want to tell people about. There are a bunch of others that I will skip in the interest of time. And yeah, if there are any more questions, I'm happy to answer. I'm also happy to answer things offline. And we'll stop here otherwise.
So questions. So what's magic about OR? I mean, what if you do AND? I guess AND and OR could have like maybe symmetric, like for for gap, for structured vector. If you add an AND reduction, maybe some other threshold. That's something that.
Yeah, the other thresholds will probably be harder, but OR and AND, yeah, AND would also be fine. If you can do AND reductions, yeah, AND would also be fine.
At the end seems like definitely for SVP, an AND would be kind of a natural thing that if it's short on all of them, definitely it's be short in the make your life easier. But I know.
Yes, that would also be great. Yeah.
Maybe we can squeak in one more question, but then I think it is probably time to let everyone go.
Interesting.
I'll just leave this here.
That was great. Thanks. It was very interesting. Thank you.
All right, cool. I will declare this BUsec over, and I guess stay if you want. I'm gonna have to go soon, but y'all can stay and chat if you